Okay. Need this? Yes. It's too much technology. Welcome back. A couple quick announcements. So you got a midterm coming up next week, this time next week, in class, open notes. We are going to post some practice materials tomorrow, and then we're going to have an extra sort of review session, if you like. Michael and Ani have offered to do that on Tuesday after class, so we'll do it at, you said 7 to 9 p.m., room to be determined, right? If you have any questions about that, but hopefully a lot of questions will be answered when the study materials go up. You'll see some of the old exams. Good. Okay, so we started talking last time about walking, and there were a couple of specific things that came in with walking that we hadn't talked about before, the idea of stable oscillations and the ideas of impacts. Those are going to be, especially the ideas of impacts are going to be general if you want to start talking about manipulation and other topics in nonlinear control for robots. These are going to be ideas that transcend walking, but walking has some really nice simple models that we can get our head around and think a lot about. So today I want to take what we did last time, the basic sort of understanding of the dynamics that we got last time, and try to start looking at the same dynamics but with the lens of computational algorithms. Okay, so last time you'll remember we talked a lot about the rimless wheel. Right, which was our toy model of a wheel on a slope, gamma, of a simple pendulum, basically. A point mass with some spokes coming out of it. Okay, that was rolling down the hill. And one of the remarkable things about that system was that even though it was completely passive, it quickly fell into one of two stable solutions. One of them was standing still, and the other one was stable periodic motion. Even if it was started very quickly, it would slow down and it would always roll at the same speed, right? And the way that looked, you remember, because this was a pendulum, we could draw it. We moved the coordinates on us just because I wrote it on the upright, but we still have the homoclinic orbits we're familiar with. It's just now centered around the origin. We had a couple of big important places in state space here, which is when one of the feet came around and hit the ground. Importantly, it's asymmetric, right? So this one was at gamma plus alpha, and this one was at gamma minus alpha, where alpha was the half of the inner leg angle. And we found that the solutions to the system here were familiar. The stable limit cycle was an oscillation that looked like this, slammed its foot into the ground, and then had a reset map that brought it back to this, because we just rewrote the coordinate system around the new stance foot, and we had a stable oscillation like that. Okay? So this was the one system, the one walking system where we could completely solved in closed form, right? For instance, one of the things we talked about was the ability to analyze the stability of a limit cycle by analyzing the stability of the Poincaré map. Which was an n-1 dimensional map. Right, so whatever our state space was, it was one lower dimensional map, which went from sort of the reduced dimensions, I'm calling it x Poincaré, xp at time n, at crossing n to crossing n plus 1. Right? This is a discrete map that, for instance, would go from the time one of the foot left the ground all the way back to the next time when the foot was leaving the ground. Okay? We could have taken it around some other point as long as all of the trajectories transverse through that Poincare map, then I can extend some of the stability properties of this map to the stability properties of the original system. That's a big time idea. Because what it did was it allowed me to do fixed point analysis on the map. Told me about limit cycle stability of the original system. Does that make sense? Maybe surprising that you can make that sort of, you can lift up and make a statement about the higher dimensional system, but I think hopefully the machinery makes sense. There's a snag though. If we start to go to implement this for more complicated systems and try to sort of use our Poincare map in order to infer something about the more complicated systems, the snag is that we'll almost never be able to write down P in closed form, right? In general, getting the solution of the system from going from one crossing of a surface of section to the next means integrating the equations of motion along some solution, and that's something that we typically can't do, right? We could only do it here because it was a passive system. We used conservation of energy, and it was trivial to do that. But in general, we can't do that. Okay, so what do you do if you can't write down P? Well, there's simple things like you can do numerical integration, and you can estimate P by running lots of simulations, even doing our sort of sensitivity analysis that we did for computing gradients of trajectory optimization. There's ways to sort of work with numerical versions of P. But I'm going to advocate a slight generalization on Poincare maps that's going to make everything work a little bit better today. Okay, and so, yeah, so the goal for today is to sort of generalize these tools to things that are going to work better with our computational objects. All right, so in fact, what we've done so far, our major tools so far have been well, let's say LQR feedback, then we did some Lyapunov analysis, and we did trajectory optimization. And in fact, you're going to be able to do all of those for these systems that have limit cycles and impacts as well. Just for fun, let's go through them in the opposite order. We'll mix it up. Okay? All right, so let's think about trajectory optimization for this sort of walking system. And let me ask even sort of a simpler question, which is, so the rimless wheel doesn't have any control inputs, so maybe trajectory optimization isn't, designing a control input isn't so interesting for that. But there's even a sort of a fundamental question you could ask. How would I find, let's say I had a more complicated system, how would I even find a stable limit cycle or a limit cycle that exists? How would I find a periodic solution? Right? So if it's as stable as the rimless wheel, you could just start simulating and hope that it falls into the limit cycle you're looking for. But our goal as control designers is to do things like stabilize the unstable systems, right? So that's not going to necessarily work, right? In general, we might want to find a periodic system that requires some non-zero control input in order to make it a periodic solution, right? How can we find that? Turns out you can formulate this problem and many more with the tools from trajectory optimization. And I hope this doesn't surprise you, but maybe it's a reminder of just how general and potentially powerful the tools we've already started to show you are for thinking about dynamical systems. Okay, so if you think about our rimless wheel example specifically, let me zoom in just a little bit on the base portrait. Okay, there's a couple things going around here. A couple things at play. We have our equations of motion, which we know were just ml squared theta double dot. It's minus mgl sine theta because we flipped it upside down. Okay, so we have our equations of motion. We have our discrete reset map, which we figured out turned out to be simple just by conservation of angular momentum. It turned out to be that the velocity just after an impact, which I was writing as theta dot plus, or maybe, yeah, that's fine. Just turned out to be a simple function of the velocity pre-impact. Okay, so we can do trajectory optimization on this. If you think about what it takes, let's do one of the direct methods. We could do a direct collocation or a direct transcription. But my state space here, of course, is just theta and theta dot. You can imagine listing out decision parameters. Let's just list out the state. We don't have any control here. I could do x0 to x big N. Okay, and let's just start leveling the constraints against the problem, right? So I want to find some solution that has, well, let's say my initial condition should be somewhere. I don't know exactly where it's going to be. I want to find whatever the right periodic cycle is, okay? But it's going to be somewhere along this line, let's say. I could say that theta at time 0 had better be somewhere on this switching surface. I could say that theta at time n had better be on this switching surface. Okay, I could say that that my update map had better hold. Wherever I end up on the end here had better be a reset map away from this, right? It must be that theta dot at 0 had better equal cosine 2 alpha theta dot at n. Okay. Of course, I need my dynamics to hold. I need my x at n plus 1 had better equal f of x at n. Can you think of anything else we need? Yeah.
Quick question. So we're constraining the initial theta and the final theta,
Yep.
And then we have our update map. Isn't there a problem if we have like a fixed time step?
Okay, good question. Right. So what happens if my my time step didn't quite match exactly this? Yeah. No, you're right. Absolutely right. So I didn't even think to say that because our formulations eat these dynamics and allow dt to be a decision variable also. But you're right. I should put in the time step as a decision variable. Good call. What else? Is there anything else you need to say? It's exactly that kind of thinking. What else would we have to throw in here? To be a solution of interest, it better be, I mean, if you think about this, all I'm saying right now is I'm telling the program to throw down a bunch of points, and then it's going to have to pull them into something that's dynamically consistent. It's going to pull one of those points here, one of those points here, but I haven't actually told it that any point that hits here gets reset, right? I haven't sort of told it all the rules of the game yet. So in order to be valid, I better also say that all of those intermediate points are not actually at the switching surface. Yeah? So let's say that for all I, let's say for I 1 to n minus 1, theta I had better be less than this. And similarly, I could say that 2 to n theta I had better be greater than that, the other side. I don't really need that nth one or the first one because those are already constrained. But okay, so this is an easy, this is just exactly a trajectory optimization problem we've already seen, but I'm just giving it a few extra constraints. One is that it starts and ends in a particular part in state space, but I'm only constraining the position, not the velocity. Okay, and the second is that this rule here, this update rule, gets enforced, and that's going to constrain that it's going to be a periodic solution. And then I can just go and ask the optimizer to try to figure out, find any solution to this. I could put in an objective, but it happens to know, it happens that we know there's only a unique solution in this for this particular problem, so I don't actually need an objective. If I can just find any solution to that, that satisfies those constraints, I should have found my limit cycle.
So it's okay that there's going to be probably a unique solution to that, like we saw, like the optimizer can still find it if it's like a general like that.
If it's what?
If it's like you're telling it to search over a constraint set that's like.
My objective is 0, and so if it can find any solution to this, it'll be happy.
I know, but like your solution set is that particular limit cycle that we're looking for. That's like a 0 dimension, like a lower dimensional space. The optimizers can still do that.
Yep. Yeah. I mean that's always true of constrained systems, right? Of constrained optimization. Yeah. Okay. So I mean, I did exactly what we just said. I said theta 1 is gamma minus alpha. Theta n is gamma plus alpha. Theta 1 dot this is my periodicity constraint. I said let's keep the theta in the range for all the intermediate points. I have one extra state just because for my animation, just to make it look cooler, I actually keep track of how far it is down the ramp. I said the initial condition 0 for that. Almost all this code is just to plot it pretty for you. So like line 25 to 50 is just to make it a pretty plot for you guys. 51, look at that. And then I solved, right? Okay, here we go. I forgot I rebooted my machine, so I gotta wait for Simulink to load. Okay, it's a trivial problem for the optimization. Can you guys see that well enough? I can't. So I just plotted that those red distracting things are just the vector field, just for sanity. The green is my homoclinic orbit here. This is just some constant energy orbits, just for reference. And it really does happen in, I mean, this is sort of an easy problem for the solvers. If I plot every iteration of the algorithm, you're going to see there's a few of them that are off the screen. It converges basically in 3 or 4 steps. Okay, boom, finds the limit cycle. Yeah, it understands the dynamics, right, in some way. It's got the reset. It's found our periodic solution. Okay, now that's a recipe that we're going to have to generalize it a little bit just in the way that I wrote down the constraints. But that's a recipe that's going to be able to work for very complicated systems, potentially. Okay? that make sense? Yeah. All right, so let's generalize it a little bit to make it work for something that's not just, always at gamma minus alpha to gamma plus alpha, right? There's a slightly more general picture you need to have in your head when we talk about systems with impacts like this. Okay, the more general form, and this might be too general. This might be general to a flaw. Is as an autonomous hybrid system. Okay? So in general, what you're thinking about when you're thinking about these systems with instantaneous events, the picture you might have in your head is that you have some continuous trajectory. Okay? It's governed by some continuous dynamics. Let's call it F1 of x. It could even be dependent on you. You could have control inputs. That's fine. In your state space, though, in general, we have some event surface, right? So we're typically parameterize that as some function, the zero set of some function. Okay? And then I have this discontinuous event, and I start up again being smooth in my new, potentially different dynamical system. Okay, F2 here. That reset, of course, has in general some rule that governs it. Okay, this is sort of the general picture that you might have in your head for a hybrid system with an inelastic collision or impulsive event. Okay, all these things have names. All right, so this is we call the continuous phase of these the hybrid modes. This is mode 2. Okay. This thing's called a guard, typically. There could be many of them also. This thing's called a reset map or a transition map. And then I'm on to my other continuous mode, right? So in general, you can have multiple modes. You can have multiple guards per mode. There's different events that could happen. But you only have one. You have exactly one reset map. For every guard. Okay, so you could think of what would be a case where you'd have potentially multiple guards, multiple resets? I mean, imagine, I always like to draw this little robot foot coming in, right? Does that look like a robot foot? I don't know. Okay, so imagine, there's a point here where the heel hits the ground. Right, but you could actually, depending if you're maybe if you're a barefoot runner, your toe hits the ground first or something, right? Or midfoot. Okay, you could have simultaneous collisions if you're perfect. Okay, so there might be multiple events, right? So there might be a guard which is set by the y height of the heel equaling 0. And there might be another one which is the y height of the toe, which is a function of x equals 0, right? So you can imagine having a whole graph of possible transitions, right, where I'm in the swing phase, and I could transition to the heel only phase, and then maybe if things are going well, then my toe comes on the ground, which is my flat foot phase. And then maybe I get a toe only, I get a heel off. And if I've got only one leg, which is all I've drawn, then maybe I'm right back to swing again, right? You could imagine doubling that, right? Okay, so you can imagine transcribing this into a trajectory optimization problem, right? So if I were to enumerate some points and say I'm going to have, let's say, 10 knot points in mode 1, okay? And then I'm going to have this jump, and then I'm going to have 10 mode points in, some 10 knot points in mode 2, and then maybe I have another jump, okay? If I know, if I can preordain a schedule of modes, then transcribing this into a trajectory optimization problem is easy, okay? If my mode sequence is known, formulating the optimization is easy. Okay, you have to sort of pick, I'm going to just go ahead and say, you know, these states are all subject to the dynamics F1, mode 1 dynamics. These states are all subject to the dynamics F2, right? Then there's a transition here where the reset, you know, this point has to be at phi x equals 0. You know, these points had better have, say for all of these, maybe I better have phi of these had better be greater than 0, saying I'm not in contact yet, right? Same way we did last time, okay? It turns out to be a lot harder to have to figure out the modes. If you don't know which, if you don't have an a priori assignment of knot points to modes, then that turns out to be a harder problem. Okay? I'll talk about that some more in a minute. But does that make sense? You could just write that down in a very general way. If you can just describe your modes of your system. In fact, if you have a rigid body system and you know that you want to, if you want to write down the reset map that takes me from this mode to another mode, and they're both given by Lagrangian mechanics, and it's sort of the generalization of computing the reset map for impulsive collisions, if I know the pre-mode and the post-mode, is actually pretty straightforward. It turns out to be a lot harder if you don't know the post-mode. We tend to have an optimization solve that dynamics for us. Okay? I'm tempted to write more, but I feel like people are looking at this and still drawing it or whatever. Can you imagine writing down a problem that given that formulation? Okay, so you know, just to say it, so say it again here, but you know, for rigid body systems, if you start giving me the constraints, I can generate the dynamics, the impulsive dynamics, from these guards if I know the pre and post modes. And it really, it's not maybe worth me deriving, but it's you just have to solve for the forces that impose this constraint instantaneously. They turn out to be impulsive forces. If I haven't put it already in the appendix on the robot dynamics, I'll put it in tonight. It's a pretty simple derivation, okay? It turns out, though, that knowing the pre and post modes is not as simple as you might think. So for instance, if you have frictional contact, okay, so if I'm throwing a robot foot at the ground and there's friction, or there's limits to the friction, then I might not know a priori whether if I come in at a certain velocity, if I'm going to sit and stick or if I'm going to slide immediately. So I immediately don't know necessarily what the post conditions are going to be, and in that case, it's harder. And if you have, depending on your representation of friction, you can get pretty complicated stuff pretty fast. So a lot of times, people will actually use optimization to simulate those to solve that dynamics. Okay. But if everything is known, then trajectory optimization is pretty easy. Okay. So let's see a slight generalization. Okay, now we have, in general, a hybrid trajectory optimization, okay, where I make a system that just has, I enumerate the hybrid modes. And we can add state constraints, add costs to each mode, okay, but I have a specific ordering of the modes. I have to say the initial times for each segment, okay? Okay, but this is now the compass gate model, and I ask for it to find a control input, U. That's not what I was going for, but that'll work. Okay, to find the solution that it's going to take exactly one step, find a periodic solution of this slightly more complicated walking system. Okay, now this one, you'll recognize this. Okay, this down here, that's the stance leg. That's the theta versus theta dot of the stance leg. Okay, it looks just like an upside down rimless wheel. Yeah, this is the swing leg. Okay. When the foot comes around and hits the ground, there's an instantaneous loss of velocity, and the swing leg becomes the stance leg. And then there's an instantaneous loss of velocity. It's the same impact event, but on the stance leg also has an instantaneous change of velocity, and it becomes a swing leg. Okay. The reason those dashed lines are like this are potentially confusing in that way. And the reason the colors are the way they are is that we're actually optimizing over half of the trajectory, and just mirroring it. Okay, but that easily finds periodic solutions of the compass gate walker. Okay, so I think, in fact, people have demonstrated incredibly complicated and impressive, whole body humanoids running in very natural gaits using almost exactly what we just talked about, right? You start getting into issues where local minima become more of a problem. But if you can find, let's say, a motion capture seed or something like this and a reasonable dynamic model, people have done amazing things with this. Okay, the limitation before has been that you have to know the mode schedule, and there's been work trying to back out the mode schedule even from like motion capture data. If I have a model and I have motion capture data, can I try to find the hybrid schedule that sort of resides in that data, even though it's noisy, right? But nothing's perfect. You don't actually hit the ground and stick, right? So there's been work like that. There's also Michael's early work has been trying to do trajectory optimization without the mode schedule, and he's generalized that in a nice way. And the key observation, I wasn't going to go into the details, but the key observation is that if you, instead of writing it down exactly like what we've written down, you write it down as a system that has control, the contact force is always being an extra decision variable, and you try to solve for the constraint forces at the same time as you're solving for the original system. And that's allowed his to think of it as sort of a single mode system, if you will, where the forces now are either active or not active, depending on if the constraints are in play. And I was just going to show the highlight reel for that. All right, so there's a group in Florida. A good friend, Jerry Pratt, has been building these lots of amazing robots, but this is the one that Michael and I were thinking about before. That's Fast Runner. He's building a robotic ostrich that's supposed to run 55 miles an hour. It's just awesome. That's their simulation. It's actually, this simulation is open loop stable, which is incredible. Michael's optimization generalized this notion of trajectory optimization where we didn't know the mode schedule, and there's a couple highlights from applying it to different problems and manipulation and contact, but he actually got it to work for this incredibly complicated fast runner model. Okay, our animation isn't as pretty. But you could take Fast Runner, which I didn't quite say how complicated Fast Runner is, but Fast Runner has, let me stop it actually and just say, so if you look at Fast Runner here, it's a beautiful piece of machinery, but you might not realize everything that's going on here if I don't say it. So there's a motor, one motor per leg, okay? The rest of the dynamics is completely a function of springs and clutches, okay? Which I think somehow is playing in the back. That's what I thought I was going to play it, but it's playing the audio from that, but I don't actually know why the video stopped. Okay, so this system, I should open it up. It's just too cool. Okay, now it's going to. So this is the initial prototype leg where there's actually no motor, no controller. There's a guy named Johnny who's shaking the leg at the top, okay? And the rest of the dynamics of the leg are just by springs and clutches and 4-bar linkages and Tygon tubing and you name it, okay? So it's an extremely underactuated system, one actuator per leg, and extremely complicated system where the number of possible hybrid modes here, we counted as 4 million or something like this, because every one of those little clever mechanical designs meant a new joint limit, a new new clutch that was engaging or not engaging. These were all hard limits, impact events in the system. So the idea that we could write down a hybrid mode for this schedule for this was just dead on arrival, and that's why Michael innovated this sort of way to do mode-free optimization. So it was a major success story for us to be able to say that we could eventually not only plan nominal gates of Fast Runner, but you could actually do things that the open loop thing couldn't do. You could have it planned over intermittent terrain and the like. Okay, so pretty cool. So I show that because I want you to realize that these optimizations, they work for rimless wheels and compass gates, but they actually scale pretty well. This is a local solution. You're solving for one trajectory of the system, but you can solve it for pretty complicated systems, subject to local minima. And that has been less of a plague than I would have originally predicted. Okay, any questions on that? Yeah.
It seems in this Fast Runner model we have also close camera chains. How can you approach such constraints from the framework?
Awesome. Good question. So, so closed kinematic chains, you can actually write down the dynamics explicitly. So you don't have to enforce them in the numerics. If you don't, you can actually write down your equations of motion for the constrained system and solve them away. If you chose to, you could also just list that as a constraint in the optimization, and it would solve that for you. But so inelastic constraints we end up having to solve with optimization. The closed chains, it's using the same math. You have a kinematic constraint. You have some force that's being applied at the joints to keep that constraint active. But in the case of a closed kinematic chain, you can solve it away. So if you're interested, there's a simple 4-bar example sitting in your Drake folder that shows you how that works in our tool. Okay, cool. So so trajectory optimization works for hybrid systems. It turns out Lyapunov analysis is going to work for hybrid systems too. Okay, but let's think about what it means to do Lyapunov analysis for limit cycles first. Okay, so like I said, last time we did this Poincare map idea. But we needed to know the map. So I want to do a generalization of this idea today. That's going to help our Lyapunov analysis. All right, the generalization is basically the idea of a moving Poincare section. Okay, so the picture I'd like you to have in your head is that when before we had a cycle, right, and we picked a Poincare section, and we just made sure that we were going through the section at all times, right? Now we're going to make a new construction, which is some section that potentially is defined along the entire trajectory. Okay, so we're going to have a moving section. It's a bad attempt at a 3D plot. Can you see what I'm trying to say? Yeah? Guess I should just do it in 2D. It's probably cleaner. How about just that? Yeah? Much easier. Okay, so you can imagine that the sticking point of knowing P was that I had to somehow be able to integrate all the way around the cycle, right? If I can somehow have my Poincare map analysis move with me along the cycle, then there's some hope that a differential, looking at just the local equations of the system and having them hold some property on this moving section could impart some of the same stability guarantees that I had on the original Poincare map. Does that make sense? I want to turn something from a integration requiring system to something that I can look at and instantaneously look at the dynamics of the system and infer something about the stability properties. Okay? So the way we're going to do that is we're going to define these moving sections, and really we're going to define a new coordinate system. My original coordinate system being x as a function of time. I'm going to map that into sort of two variables now. Tau, which is my distance along the trajectory, sort of my phase in the trajectory. And then the coordinate that's somehow orthogonal to the trajectory. I'll write it down as x perpendicular. This is going to be my n-1 dimensional. We call them the transverse coordinates. Okay, and if I have my original dynamical system, x dot equals f of x, I can always rewrite those dynamics on this new coordinate system. If I have the mapping between those defined, I can write tau dot, which is going to be like something, if tau is a surrogate for time, it's going to look like time to first order plus maybe something else. And then my x perp dot I can write down too. It's just a new coordinate system, but I'll choose a coordinate system that moves along the trajectory like this, where one of the dimensions is exactly on the trajectory, and the other coordinates, they don't actually have to be orthogonal. They just have to be linearly independent from the velocity vector at that point, the flow vector at that point. Yeah. Okay, so the question is, what can I say about the dynamics on this surface to say something about the stability of the limit cycle on that surface? Okay, well, it turns out that the same sort of notion of Poincare stability is going to hold in this case, right? So there's sort of powerful theorems. Which say that if I can produce a Lyapunov function that's just a function of my transverse coordinates, which is, in general, is my greater than 0 when you get into all the Lyapunov arguments and variations thereof, okay? With v dot less than 0, in the simple case. But notice this doesn't depend on time, right? This is just a function of my perpendicular coordinates. Okay? Then stability inferred here imparts a statement about orbital stability of the original system. Okay? In this case, it's exponential, or it's asymptotically orbitally stable. So specifically, if I defined x perp to be this metric that I was talking about before, then I'm going to have orbital stability, if you remember, limit cycle stability, orbital stability, meant that that went to 0. Does that make sense intuitively, right? So what would you want to do? Okay, so we want to somehow, I originally had Lyapunov functions that decayed to the origin, right? Now what I'm trying to do is come up with some function which decays to the orbit, right? So if you can imagine some function which is, let's say, ideally 0 along the entire limit cycle of interest, and you can show that it's going downhill all the time, then by the time you're done, you're going to get to that orbit, okay? And then if it's an orbit of a dynamical system, then I've got some dynamics in tau. That means it's going to be a stable limit cycle. In fact, it doesn't have to move around the cycle to be orbitally stable, but almost always tau. If tau is a surrogate for time, it's going to move along that cycle. Okay. The definition of orbital stability says the distance between my state and my orbit goes to 0, and that can hold locally. That can hold regionally, that can hold globally. Sorry. Yeah, no problem. And that can hold, it can be exponential stability, asymptotic stability, even stable stability in the sense of Lyapunov. Okay, so the picture you should have in your head, which maybe I'll avoid trying to draw, is a well, your Lyapunov well that goes through, okay? So it turns out it's going to be possible to construct that in sort of reasonable ways, okay? So in particular, there's another very nice theorem, which says that my dynamics, I just said you can write down your tau dot, let me just write it as F1 and X perp dot. Okay, I can approximate this. I can always linearize this dynamics. And give myself something that's known as the transverse linearization. What's that? Thank you. I can just Taylor expand F2. Tau dot, it happens if you Taylor expand it, is going to be 1. Okay. And maybe the most important or surprising result here is that this now looks like, well, what does that look like? What have we seen before that looked sort of, took that form? The time varying, when we did time varying LQR, right? This looks like, and in fact, we can apply all the tools from linear time varying linear systems to construct a Lyapunov function using a Lyapunov equation that will prove stability of this time-varying linear system, and then that'll impart local stability of the original nonlinear system. Okay. Go forward. So, if my transverse linearization is stable, then there exists a unique positive definite solution. This should sound familiar, but it's an extension. To this, it's a unique periodic positive definite solution. Okay. To my Lyapunov equation. Pick any positive definite Q to throw in there. Give yourself some shape. That's your design parameter. Okay. But if you pick a positive definite Q, you find a periodic solution to this, some periodic P, right? Find there's exactly one, which is periodic and positive definite. Then the Lyapunov function proves orbital stability of the system. Okay, so if you remember, I know you're all writing, so I won't say anything super important for a second. It's important. If you remember, for nonlinear systems, we had to invoke big tools like sums of squares to try to find Lyapunov functions or just be really clever. Okay, but for linear systems, we could just write down the Lyapunov equation, solve an SDP, or that's the harder case. You can just solve the Lyapunov equation with specific methods. Okay, and that gives us a Lyapunov function for the linear system, which, you know, if the linear system was stable, if and only if the linear system was stable, you can construct a Lyapunov function with that tool. That same thing's true here in the transverse linearization. Okay, that we can find this. That if that system is stable, then we're going to be able to find a Lyapunov function like this. Solving this for the periodic solution can be a pain. Okay. Fortunately, now this is sort of a cop-out, but every time I've ever tried this, I've been able to just simulate it until I found the periodic solution, and that was okay. And maybe there's something magical in general about that. I can't prove it. And there's people that spend a lot of time thinking about the existence of that, or numerical tools for finding that. But so far in life, I've been able to get by just simulating backwards in time until it converges to a periodic P. Okay, this is just a differential equation. You simulate it until you find a periodic solution.
That was always true.
You think it's always true? I think there's people that prove that it. I don't know if it is. Yeah, there's people that think a lot about it. If it was trivially true, then
I don't think it's trivially true, but
You think it's always true?
I thought it was known to be true.
Known to be true that it's stable?
That
That differential equation converges? It's possible. It's possible. In which case, it wasn't just luck. Okay, so Ani thinks that it's always true.
I could be wrong.
Yeah. But Ani could be wrong, and now it's on the record. Okay, so and similarly, you can take this the same way we did our region of attraction estimation on nonlinear systems around a fixed point. You could, for instance, invoke sums of squares to check some of these conditions. You could start with a linear system approximation to recommend a Lyapunov function, which is now a construction. It's a bowl around my trajectory, okay? And it's one that I could optimize with sums of squares. I've got some nice examples of that for the rimless wheel. Well, let's think about the rimless wheel first, okay? But, well, actually, there's something important I didn't say yet. So,
how do I do this for, how do I do transverse coordinates for hybrid systems? Okay, so now I have my pictures back here. I've got my switching surface. Okay, if I can design some set of coordinates which is everywhere transverse to the trajectory, but it need not be exactly perpendicular. This is where that extra richness comes in. If I can line up my switching surface with the transverse surfaces, then I can still make some of the statements that it gets around a lot of the complexity of trying to understand. It turns out if I can write down a Lyapunov function in a transverse coordinates where the transverse sections never intersect with the surface, then I can do all the same tools where I now solve a jump differential equation. My Lyapunov equation that I'm going to simulate backwards is smooth here, and then for one step I solve the discrete time differential equation, and then I simulate backwards here.
I don't mean to have you, I mean, I don't want you to not understand it, but that's just, I just wanted to give you the cartoon for that. Riccati or Lyapunov equation in the simpler case. Okay? Yes?
I have a question from 2 slides ago, sorry.
Okay, I think I can do that.
And the definition of X transverse,
Yes?
is that supposed to take the value of the distance between the inside, or is it supposed to be the higher dimensional? Sorry, or is it supposed to be just the norm? Or is it...
Wow, good catch. So it is the X, so I should not have written it quite like this. X perp is defined the tau is defined like this, right? It's the argmin of the tau. I wrote that too quickly. And then X perp is the projection onto that coordinate system.
So it's the inside of the norm for that tau.
Yeah. We have some moving coordinate system there. It is not the distance, it is the coordinate in that space. Yeah, those two equations should not have looked exactly the same. That was writing too quickly. Yes?
So when we move from n-dimensional to n-1 dimensional system,
Yes.
how do we know which dimension to get rid of, or how do we choose this?
You have some freedom to choose the coordinate system, but the one you get rid of is the one along the trajectory. Right? So your first vector is given to you, the one you're about to throw away. That's the vector that is my instantaneous direction of travel. Yeah? Throw that one away, but build a new coordinate system. You know, you can pick an orthogonal basis that starts with that as the first vector that you're going to throw away. Build up your orthogonal coordinate system, or more generally, if they have to line up with switching surfaces, you can pick some basis set, which the dot product is, or the cross product is non-zero with this, I guess. Yeah, it's linearly independent of that vector. All right, so let's see how that could play out for the rimless wheel example.
Okay, so the rimless wheel turns out to be a great example for this because there's a trivial choice of coordinates, of transverse coordinates, right? I can just pick my transverse coordinates to be the coordinates where theta is constant. And I can define my x perpendicular is going to be the theta dot coordinate, but relative to my, I want to put it in a coordinate system that's relative to my nominal trajectory. So it's relative to my trajectory of interest, which is parameterized completely by theta. Theta is now taking my, the role of tau. And x perpendicular is going to be the difference left there. Theta dot star. Thank you. Okay, so it turns out you can just differentiate that, insert my dynamics, right? To write down my x per dot is just going to be theta double dot minus theta double dot on my coordinates, right? Which turns out to be something simple. And shockingly is coordinate dependent. It's time varying, sort of linear already. I don't have to take a linearization. So let's think a little bit about what that object means. So is the system is it stable? We know it's stable, but does it look, I mean, look at this as a linear system. This is literally a scalar in this case, right? It's a two-dimensional, n is 2, so n minus 1 dimensional is 1. My transverse coordinates are one-dimensional. This is x dot is minus a scalar times x. So it's going to matter, the sign of that scalar is going to matter if I want to ask myself if it's sort of stable, right? So what's the sign of this going to look like? What's the sign of that thing? Theta dot star is always positive on my nominal solution. So the denominator is always positive. Theta is going from a negative number to a positive number, okay? So this thing is actually, this is negative, which means this whole thing is positive. It's sort of up here, trajectories, if you draw those, you won't be surprised, right, when you draw the orbits, right, but things sort of diverge on this side and they converge over on this side, okay? So instantaneously, and this brings up a point that you were raising not too long ago, was instantaneously these trajectories can be diverging, but I can still find a Lyapunov function that over the period is going to prove stability, right? So it's diverging locally, it's converging here. The major stabilizing event is at the dissipation, okay, is at the impact, okay? But I can still find, even though this coordinate things look to be diverging and this is contracting, I can still find a Lyapunov function which is going downhill all the time and has a periodic solution, okay? So for the system to be, stable over the period is different than it to be stable always, at every instant in time, right? I can go away from my trajectory and come back, and I can still find a Lyapunov function that would prove that. Okay, that's a very important idea. Okay, and we can take all these tools, and we can, if we like, we could throw them into sums of squares and estimate the regions of attraction. Okay, we're not going to ask you to do that, but it's certainly doable. And let me show you some of the pictures that maybe help you see that. Okay, so this is that same picture I just showed you. This is the phase portrait. This is my nominal limit cycle. Zoomed in a little bit here, okay? The pink is the region of attraction in phase space of that limit cycle, right? So remember how you could actually be going backwards and still find your way over? You can sort of see it in this picture, right? If I have enough velocity, then when I come over, I transition, I can be above the homoclinic orbit over here, just because that whole thing is shifted to the side, right? And start coming in. So it's a pretty non-trivial basin of attraction. And it goes off to positive velocity infinity, okay? If I define my coordinates like this, and I ask for the Lyapunov function by solving this linear equation, this Riccati equation backwards in time, and then I just check when does that work with sums of squares, then I get a reasonable estimate of the basin of attraction. If I search for even a higher degree polynomial that satisfies that, using the linearization as the initial guess, this is what you get. Okay? These are my moving Poincare sections. At every point, you check that the Lyapunov conditions hold, and you search for a Lyapunov function that maximizes the volume of the estimated region of attraction, and you can get things like this out. Okay? We've never gotten that. That's tough, right? But there are places here that are pretty subtle where you're actually your tau is going backwards, right? So you're actually over here in the coordinates of the cycle, you're going this way in the cycle before you come back this way. So the conditions don't require that you go one way through through the switching surfaces, but they do require that everywhere you're going downhill on x dot, which means you've got some, because these things diverge over here, you've got some, you know, non-trivial Lyapunov function that's allowed to go downhill even though it's expanding and then comes back. Okay. These things, the sums of squares techniques for this, we've done only modest systems so far in our group, in the hybrid, but it was, you know, some of the first tools that exist for estimating regions of attraction to hybrid limit cycles. So I think we'll get better at it. But right now, this is the actual region of attraction step is only going to work for simple systems.
Okay. Last idea now is a simple extension of what we just said to some extent, right? So let's say I've got my transverse linearization. But let's start with a control system now, where I have control inputs. I have some trajectory, and maybe it's periodic, maybe it's hybrid, okay? And I've constructed some transverse coordinates that I'm driving through, so I can write my system down in the coordinates x perp dot tau dot. Okay? If I linearize the control system, I've got a U here now too. Okay? I can approximate this as a time-varying linear control system. I don't really want that. Okay? And I can design an LQR controller on this time-varying system. Okay. If I line up my switching surfaces with my transverse coordinates with the switching surfaces, then I can solve through impacts and the like, and I can do LQR along a trajectory. And the result of doing it in this reduced coordinates is to get orbital stability of the closed loop system. Now that's actually a really nice idea, even for, it's certainly, if I want to have a system that's limit cycle stable, this is a way to get it. But let me try to convince you that actually this is an idea that might have power beyond even periodic solutions, right? So one of the annoying things about LQR and time-varying linearizations is that if I have some state here and I'm trying to track some trajectory, let's say I'm off my trajectory and I get a little bit behind in time, right? The TV LQR we've talked about so far is trying to reduce this error should be red, right? It's trying to make this error go to 0, right? And it can be really hard to generate controllers that can catch up with time, especially if you're an underactuated system, okay? And in practice, the gains of the controllers that you get out of a TV LQR can be high because it's trying very hard to do something off the trajectory that it maybe could only do on the trajectory, catch up in time. You'd like to think, okay, well there's an obvious solution to that. Let's just project down, and when I'm running the system, let's just project down and use this as my
I'll just remap time as I'm executing my time varying linear controller, and I'll use that as my error. I've got my u equals k times time x. Maybe if I just remap time as I'm going, that would be okay, but you actually can't do that. Sometimes you can do that and get away with it, but there's simple examples where that will destabilize the system. It turns out stabilizing the transverse coordinates is maybe the right way to get a time independent, to make yourself safe under this projection so that you can search for the trajectory, search for the closest time in the trajectory, and execute a controller that tries to get me back to this and drive this error to 0, okay? So it turns out if you stabilize the n-1 dimensional system, then what you're really stabilizing is the error dynamics in the projection to the closest point on your trajectory. Does that difference make sense? This is something that everybody who tries to do TVLQR starts asking this question, like, okay, at some point you're looking at the way the system's performing, it's trying to keep up, it's working too hard to do that, what can I do to make that better? And most people just try to hack it, and then sometimes they get themselves in trouble. It turns out that the right thing to do is to stabilize the n-1 dimensional system. Okay? And if you run that controller on the real system, then you'll stabilize the manifold. Now that's not, sometimes you actually want to stabilize in time, right? But this can be significantly better, especially for underactuated systems where you have limited controllers. So in practice, what you'll see, for instance, is that the controllability of some trajectory, the gains you get back in the full coordinates can be very large, okay? And if you just try to stabilize the n-1 dimensional system, then you might get numerically much better conditioned systems, much lower gains. It can make a big difference. We've seen places where it doesn't work well at all. So if you try to stabilize the pendulum, by stabilizing a transverse coordinates, there's places where the transverse coordinates, the trivial transverse coordinates, are not controllable, even though the original system was controllable. You can get yourself into trouble. If I can even tell you that story, right? So if in the pendulum, if I take my, try to stabilize this, this is my eyeball, right? I'm trying to stabilize this point. Let's say I have a trajectory that's coming in and goes like this, that I want to stabilize, and if I pick this as my transverse coordinate, right, there's nothing I can do at the end of time. I have no control authority in this direction. Remember, my control authority is only in this direction. Right? So U doesn't affect my dynamics in this dimension. So you can imagine picking a transverse section that's not stabilizable. But for trajectories, and certainly for periodic stability, this notion of stabilizing the n-1 dimensional system with LQR is a powerful one. Okay? Awesome. So in one short period, we took our rimless wheel and we figured out how to do trajectory optimization, the Lyapunov analysis, and LQR, and you can now use all your tools for hybrid systems. Yeah? Cool. I'll see you next time.